Okay, how was the coffee? I missed it. Welcome back. Just 2 minutes wrapping up. So what we did so far, and this first example was really on rapid modeling. Yeah? So the message here was really to show you that it's easy to take a journey and walk from the data to a useful model quite easily and get a lot of useful outputs, visual outputs, interactive outputs you can use to explore, to understand your data, your problem better, and then, of course, use validation techniques to get a good predictive model at the end. And we did all these steps from exploratory analysis to model screening, maybe looking into some other models which are available. And then, sorry for the cliffhanger, I said, now we can take this predictive model and use it on all the data, all the combinations. And that's the other data set which is also available on the journal. And if you look at the number of rows, 4,608. These are all the data sets. And the scripts coming with the data table show you some results. The same distribution outputs, just all the data, but very similar. Maybe more interesting are the actual by predicted plots. And on the left, we have the overfitted regression tree, then the validated regression tree, then we have the linear model, and we have the neural boosted model. And you see that this is a bit crazy here, of course, overfit. So we have values here, so it's actually less than 1%, but the model predicts 89%, so that's totally wrong also on the other end here. This looks better, and this is just one way to look at the model performance. Another way would be using heat maps like this. I also remove the legend and zoom it out. And now we can look at the heat map. Now all the combinations, we had a high throughput analysis, and we have all the measurements. So now we were lucky, so we can see the real data, but we can also look at the models and then compare the real yield measurements and then understand the differences between our different models. So that's the linear model. You see the abstraction, and then we also see the neural boosted model with more nonlinear patterns and more detail for this type of model. And then finally, at the end, all models are wrong, some are useful. So in JMP, the profiler really helps to find the most useful models and also ask questions like, what will happen if we change one factor? What will happen to our response we are concerned about? So that's the end of the first example, and with this I would like to hand over to Phil for another example. And now it becomes really challenging, not just rapid, but challenging.
Thanks, Volker. And do let us know later today if you want to understand more about how you can apply predictive modeling, machine learning in the kind of research that you're trying to do. So that was a really great introduction to all the powerful tools that there are for you to understand your data using machine learning, predictive modeling, and how it's very easy and quick to do in JMP Pro. This next topic's something a bit different. This is really quite cutting edge stuff. What we're talking about here is the application of machine learning to very small data. With machine learning, deep learning, AI, you typically think about big data, really big data. People like Google and Amazon and Netflix that have got huge amounts of data from customers, and they're trying to make sense of all of this, and they're trying to do it very quickly and get the maximum insight from these vast data sets. In science and engineering, we often have a different problem, which is that collecting data is often very, very expensive. Netflix basically, you're paying to give them your data, and they're getting vast amounts of data about you that informs them of how to improve their product, how to improve their service. And they're getting all that. They're not just getting it for free, you're actually paying them. In science and engineering, one row of data can cost us tens of thousands of pounds or euros, dollars, or even hundreds of thousands of pounds. So we have this opposite problem. So how could we use the ideas from machine learning and apply it to very small data sets? Well, this is there's a potential breakthrough in that called self-validating ensemble models. And we're going to use a simulated example to illustrate this. And our objective is to understand the effect of 6 factors on the growth rate of a biological process. So this is, it's made up, it's made to feel like it's a real example, where we're trying to predict growth rate, so that's our response. And I've purely simulated this data. And I've simulated so that each of our 6 factors has a strong effect, a strong main linear effect and a strong curvilinear effect as well. So there's quite high signal to noise here, so we've simulated it with some noise, as we get in real life science and engineering experiments. But we've simulated it such that the actual signal, the effect of the factor, is 3 times the size of the noise that we've simulated, the random noise that we're adding to the data. And so adding the intercept to this means that we've got 13 parameters to estimate, 13 effects, behaviors that we need to uncover in our data. And if we have an experiment with 46 rows of data, then that's no problem. So this example here, this is a statistically designed experiment, something called a central composite design. And you can explore that, what that looks like from this scatter plot. So here we're looking at 3 of the factors, because we can visualize that in 3 dimensions. And you're seeing how we've varied those in a very balanced, symmetrical way. This is design of experiments, and it's a topic for another day, but one that I'm always very happy to talk to anybody about. So you can see, if you actually just click and drag on this cube, you can rotate it. So you can see how we've positioned our different points across the factor space. And we've got 46 observations on this process, this biological process. So we can easily, with that amount of data, we can easily build a model. We're going to build something called a response surface model. So that's a model that includes the main effects. So is there a difference between a low setting of citric acid and a high setting of citric acid? A low amount of citric acid, a high amount? Is there just can we detect a linear change between low and high? We're also adding in the quadratic effects, the curvilinear behaviors. So is there some kind of peak in the middle of the range of citric acid, or maybe a trough in the middle, and also interactions between them. So does the amount of citric acid affect the trend for EDTA, which is another additive that we might add in here? So we'll just click run. So we've got this model. It fits very well because I simulated this data so that it would fit well to this kind of model. And we can detect the important effects. So we can see there's an important linear effect of all of our factors because that's how I've simulated it. So we should see that. And then all of these quadratic or curvilinear relationships are also coming out as important for each of our 6 factors. And then all these 2-way interactions are less important, less statistically significant. And so this is what the prediction profiler for that model looks like. Again, this is how I'd simulated it to look, so that's how it should look. So it's maybe not a very realistic model. What I've simulated there, for some reason, everything starts with a reasonably good growth rate, and then as you add more of each of these additives, it gets a little bit worse and then improves towards the end. That's just the way I've simulated it. It's very artificial, but it's for illustrative purposes. So with a reasonably big experiment like this with 46 observations of different factor settings, we can estimate a model like that quite easily. So let's just, to really illustrate what we're talking about here, I just want to ask you a fairly simple question. If we want to fit a straight line to model the behavior of citric acid on growth rate, so if we just considered one of our factors, amount of citric acid on the x-axis and growth rate on the y-axis, and we want to fit a line to model the relationship between the two. How many data points do we need to fit that line? 10? 1? 2? 2? Yeah. I remember my high school physics teacher asked the class this question once, and his answer was, and he was always you didn't argue with him, he said 6 for a straight line, 12 for a curved line, and that was his answer. And maybe it kind of makes sense, but actually, if I could go back now, I still wouldn't challenge him because he was really scary, but I would want to say that actually you only need 2 for a straight line. And then if you want to model a curvilinear line, you're going to need at least 3. Basically, you need as many data points as there are parameters in your model. So for a straight line, there's 2 parameters. There's the slope parameter and there's the intercept. So we need a minimum of 2 data points. For a curvilinear quadratic relationship, if you think, if you studied in the UK and you did GCSE maths, it would be the equation that represents that is y equals ax squared plus bx plus c. So there's 3 parameters to estimate. So you'd need a minimum of 3 data points to model that curvature. So in this case, we've got 6 factors. Each of those has a slope parameter and a curvilinear quadratic parameter, and we've got 1 overall intercept. So we need minimum 13 observations to model that. So we're just extending this kind of, sorry.
If you have information on the error distributions of each measurement, do you also provide the ensuing error estimates for all the parameters you estimate? Because that's the thing, if your noise is large enough, of course you still will have a very noisy.
Yeah, right, absolutely. So the minimum, so again, for just a straight line, if we have 2 data points, we can estimate the slope and the intercept of that, but we wouldn't have any estimate of the noise. So you typically do want some additional data points to be able to estimate the noise.
But what I mean is, can you externally plug in the information you have on the measurement uncertainty?
You could potentially, there are ways of doing that. JMP is fundamentally a statistical modeling package, so it's about modeling the data that you have and learning from the data rather than kind of imputing error.
If your data come from a device and you know just a certain accuracy, then it's important to include that in the data, but it's not the value that you measure, it's an annotation to the value.
Yeah.
And it would be good for the software to be able to cope with these types of annotation.
Yeah, there are ways of doing it. Yeah, there are. I'm not going to show that today because it's a bit of a niche topic, but yes, it's a good question. There's ways of doing that. So, anyway, just going back to what we were saying, we've got 13 parameters to estimate. That's the thing to remember here. So, let's, whoops. I don't usually use a Macintosh, so bear with me if I'm a bit slow. Did I shut down the wrong thing there? So the question is, so it was easy to identify the important behaviors in that simulated example with a 46-run experiment, with 46 rows of data. Can we do the same with 13 rows of data? So this is what we call a definitive screening design. It's a very sparse experimental design. So we can explore this again. We could look at the scatter plot matrix, which tells you, it gives you a plot of each factor versus every other factor. So you can see how, again, it's very symmetrical, it's very balanced, organized design. And if you look at the 3D scatter plot, you can now see it's more sparse. We're not covering as many points in the factor space now. We've only got 13 observations of different factor settings. So and again, I've simulated the same growth rate data using the same underlying simulation model. Let's see if we can model that using some standard statistical tools. So we could look at modeling the main effects model, where we're just looking for these linear effects of each factor. So let's run that. We can estimate that model, but it's not a good model. We're missing these curvilinear relationships, so the model is really lacking. But we can estimate that because there's only 7 parameters to estimate there from 13 rows of data. 13 data points, 7 parameters to estimate. It can do it, but it's not a good model because we're missing the curvilinear relationships there. We can use something called fit definitive screening design, and this is a specific algorithm for one of these types of experimental designs. And where there's not too many active factors, it does a very good job. But in this case, because I've simulated it very artificially to have lots of different behaviors that we need to capture, it doesn't do a good job. It's only picking up one of these factors as being important. So it's not good. This is a very challenging situation for trying to model from this small amount of data. And we could even use lasso. So this is a more advanced form of regression modeling, using AIC as a validation criterion. And it's just not picking up anything as being important. There's too much for this. There's too much that we're trying to understand from such a small amount of data. This is the real challenge. So let's move on to the next section where I'm going to introduce a trick. So this might at first seem a bit like we're cheating, but it works basically. So what we're going to do to start with is we're going to double up the rows. So we're going to take our 13 rows of data and we're going to just exactly copy those, essentially. So we've got 26 in total. So that would definitely be cheating if we just try and double up our data. That's not, that's not playing by the rules of statistical modeling at all. But we're not just going to do that. If we click on this and open up this 13-run design, which we've set up for auto-validation, so you see we've got 26 rows now, so those 13 rows have become 26, and the first 13 rows and the second 13 rows are identical, except we've got some additional columns here where the first 13 rows are our training data, and the second 13 rows are our validation data. So as Volker showed before, we can do training and validation. We can build models on the training data and validate it against the validation data. Now again, if that's all we did, that would be a horrible cheat, and that's not going to work very well. We're going to be using the same data for training as for validation, and that's just not, that isn't going to work at all. That's not a good idea. what we're going to do is the reason we're doubling up this data is we're going to use fractions of each row of data for training, and then the remainder of that row for validation. And if you run this first plot here, so we've got our 13 different rows duplicated, and for that first row, we're going to use that mainly for training in blue. So row number 1 will be mostly used for training, and we'll use a small portion of it for validation. We'll weight a very small portion of it towards the validation. Row number 2, we're going to use more of that for validation and a small amount for training. And you can see how they, if we're using it in training, then we're using less in validation. If we're using more in validation, we're using less in training. So we're not holding back a whole row or whole numbers of rows for validation as we do in normal machine learning. We're holding out fractions of each row. And again, that wouldn't work particularly well if that's all we did. But what we're going to do is we're going to build models using this validation scheme, and then we'll redraw these. So if I get these so that we can see them both simultaneously. Just reduce the size of that a bit. We'll re-randomize that. So we're selecting these weightings randomly, and we can keep doing this. So we'll build one model with the weighting like this, and then we'll redraw the weightings, and then we'll build another model. And we'll do this hundreds of times. So we'll build one model using lasso regression. And in this case, the model doesn't actually come up with anything. With those random weightings, we're not seeing anything. And then we can redraw those weights, rerun the model. And we get something slightly different, but again, in this case, it's come out as being insignificant. And I think let's just try redrawing that again.
But it's kind of a continuous cross-validation. It's quite funny.
Yeah, it is very similar to that. If I automatically ask this to recalculate, with this random draw of weightings, we've got all of these active factors in there. So then what we're going to do is we will average over all those models. We're going to ensemble those models. So this is a term from machine learning, the idea of ensembling your models together to give you an overall average. So I'm going to shut that down now. So you can look through all of this in your own time. In actual fact, in JMP Pro now, we can do this without having to set up, without having to duplicate our rows. There is a mechanism in the generalized regression platform now, which will enable us to do that. So we set up our model specification as we normally would, with growth rate as our response, and then our factors in the model effects, and we've set up again a response surface model here. And we'll click run, and we're using generalized regression as the personality. We're going to use normal distribution, and we're going to use, instead of lasso, we're going to use SVEM lasso, self-validated ensemble modeling. So self-validated because we're using the same rows of data for validation as we're using for training, but again, we're using fractions of each of them. And we're going to re-randomize those weightings 200 times. And I'll click go. And it's gone away and it's done that process. So it's essentially duplicated the rows, given them a random weighting, given them, fraction of each row for training, fraction of it for validation, and randomized those amounts. Fit a model, and then it's redrawn those weightings, fit another model, and it's done this 200 times, and then we've averaged over those 200 models. So each of these effects, the effect of each factor is actually the effect that we've seen averaged over those 200 models. In some of those models, the effect appeared to be significant. It had a parameter of a certain size. In others of those models, it was 0. And we average over all of those. And so, one of the things we can see is the percent of times that each of those effects is non-zero. Each of those parameters is non-zero. And this gives us a separation of the important factors. So we can see the main effect for all of our factors here as being important, significant. We can see these quadratic effects. So it's found all the important effects that I simulated, that it should be able to find. But it's only been able to find it by using this very clever, innovative machine learning trick. We couldn't do this using standard modeling. We didn't have enough data. But by using this self-validated ensemble modeling, we're able to understand all of the important behaviors in this system from a very small amount of data. So this is really the innovation. And we can just visualize that in this model. I'm just going to increase the size of these a little. And you can see that's the same behavior. So this SVEM model, this self-validated ensemble model, has been able to find the exact behavior that I'd simulated it to find. Yeah, question.
So once you have your model, kind of by whatever means, what's the quickest way in this software to find the combination of values for each parameter that gives like the maximum, say, growth, in this example?
Yeah.
That's the thing normally, like, we do all this to really...
Right, exactly, yeah. So most of the time we're looking to optimize growth rate, optimize yield, minimize impurities, whatever it might be. So from any of these prediction profiler visuals, so Volker showed these as well for decision trees and for neural nets. With any of those, you're able to go in and specify the idea of desirability functions. And by default, it just assumes that each response is something that you want to maximize. But if you didn't want to maximize it, then you can actually set the desirabilities. So this is something where we want to maximize it, but we can go for something. If you've got a target, for example, for growth rate. So let's just say for some bizarre reason, I really want to achieve a growth rate of 20. At the most, I'll tolerate something that's 30. So I'll give that I'll give that a desirability of 0.1. Do I need to do that in? And you can see you can set a very different sort of desirability. So 20 is the most desirable. 30 has a desirability of 0.1, and so on. So you can actually, or I can just manually adjust these as well. But let's say we just want to maximize it, so I'll just keep it set like that. Then having defined what is most desirable, you can just say maximize desirability, and it will go away and find the combination of settings that gives you that target. Any other questions? One of the things that I will just show you, I mean, within this prediction profiler, there's a huge amount that you can do. So you can actually simulate noise, for example. So we can look at, if we can't control these things absolutely, then we can understand how random variation in our inputs is transmitted to variation in our outputs. So we can simulate that and just keep that interactive. So you can see how different amounts of variation in the inputs affects variation in the output there, and how different settings will give you different amounts of variation in the output as well. So this prediction profiler is really a very powerful way of interrogating the models that you build and doing what-if scenario analysis on any model that you build.
And if you have any specification limits or external requirements set on your response, then you would also see the defect rate measured under this random variation, and then you can decide, do you want to optimize for the highest growth rate, the highest best response, or do you want to optimize for the lowest defect rate? And for this, there are also techniques built into the simulator to do this using a computer experiment.
Yeah. So, a slightly different topic that. So, I hope we found that interesting. What I really want to demonstrate there is there's a lot of advances going on at the moment in the world of machine learning. Most of it's really around how you do deep learning on big data and image classification, things like that. In the world of science and engineering, it's really about how can we extract the maximum insight from very small amounts of data. So these are probably the most important innovations that are happening now in the world of machine learning for science and engineering. And a lot of this is driven by people who use JMP and the people who developed JMP. This self-validated ensemble model was actually an idea that came out of our own R&D team. So I don't think it's something you'll see in any other available data analytics platform currently. Okay, did you want to close things off, Volker?
On the journal, there's also a section to point you to some useful resources. One resource I would really like to mention here is our MOOC. That's an open online course. It's called Statistical Thinking for Industrial Problem Solving. We call it STIPS. And you can also find it if you search for this online. And this comes with 7 modules. So they take a few hours for self-paced learning, and they have really short videos and nice examples, and also a small questionnaire at the end, and if you pass, you get a certificate that you passed one of these modules. And if you want to learn more about DOE, for instance, and there's also a module about predictive modeling, including text analytics, or some other modules like how to set up, how to define the problem and define the factors, the factor ranges, and so on. It's the first module. So they are highly recommended if you want to learn about basic concepts, or if you want to invite your students, if you are teaching, to look into these concepts. That's our open online course about statistical thinking. To get students started, professors should not teach the software. For this, we also have one-page guides, more than 100 guides on common statistical methods, just one-pagers or a very short video. And you can also get access to this either on the Learning Library. It's online here. Learning libraries, so they are all online, but you can also get the full bundle with all the guides and an analysis guideline as a single PDF document at the table. So if you contact us at the table later, so I can give you access to that one. And we also have a nice white paper to share by a US professor, Roger Hurl, and he wrote a nice paper about integrating machine learning tools and statistics, more basic statistics, and also experimentation. So really to get the best from both worlds. And this, he calls this a holistic approach to big data analytics. I think this is a really nice discussion, a good read, and you can also get access to that white paper. Using this link, you have to register, but you can also get this if you talk to us. That's all we have to share with you for now. Are there any other questions or is